invitation. Thank you for the invitation. Today, my talk is based on the work with Corey Jones. He's now an assistant professor in North Carolina State University, and Dave Pennis, my advisor in Ohio State University. And my talk is based on this work on the categorical chi. All right, so first let me start with the basic about tensor category. So a tensor category, C, is a C-linear abelian category with a tensor structure. So C-linear here means your category, the home space is a C vector space. And then your underlying category is a abelian category. And the tensor structure is associated up to isomorphism. We have a bunch of examples. For example, the category of vector space. So vector space is your object, and the morphism being the linear transformation. And you can tensor two vector space become another vector space, right? And also from the group, you can say G-graded vector space is also vector space, tensor categories. And also for group G, you can talk about the G representations. And the tensor product can be given by G act on B tensor W. If V and W are representations, then the tensor product is given by tensor product as vector spaces. And also you can talk about representation of half algebra or quantum group. They're all tensor categories. And another one, if you start with a ring, then the ring RR bimodule is a tensor category. Tensor product is given by the relative tensor product of R. All right. And since I'm operator algebraist, I care about the unitarity, which means you have a positive definite dagger structure on the tensor category. Literally, the dagger structure is on the home space. If you have a morphism F from A to B, then we say F dagger is from B to A, such that you do dagger twice, it will be itself. And then the dagger play nicely with the composition and the tensor product. Namely, G compose F, then dagger equal to F dagger compose G dagger. And also F tensor G dagger equal to F dagger tensor G dagger. And then we have many examples as unitary tensor category. For example, the Hilbert space, category Hilbert space, and the bounded operators, and the G-graded Hilbert space, and the unitary representations. And also for operator algebra M, your bimodule, MM bimodule, will be unitary tensor category. So how do we understand this dagger structure? Well, let's look at Hilbert. So if you start with the finite dimensional Hilbert space, once you pick up the basis on the Hilbert space, then your morphism from Hilbert space to Hilbert space will correspond to the matrix, right? Then the dagger of the matrix will be just the complex conjugate. All right, so literally complex conjugate to twice equal to self. And also these things just is something that you're familiar with. So dagger structure is not something really weird. It's pretty natural. All right. So that's good. All right. And we call the morphism being unitary. If U dagger U equal to identity of A and U dagger equal to identity on B. If you only have this condition, then we call it isometry. This one called isometry, co-isometry. All right. So again, if you are in the Hilbert space, then literally the unitary matrix. All right. So U star U equal to identity A, U star equal to identity B. All right. So the last thing is if a tensor category is called fusion, if it's finitely semi-simple, rigid with simple tensor unit. Finally, so here, simple object means your home space on that object is one-dimensional C vector space. And semi-simple means all the object in this category is the isomorphic to direct sum of finite many simple objects. And finite many means you only have finite isomorphic class of simple object. Rigid means all the objects have two-sided duals. And in the end, your tensor unit must be simple. Otherwise, we call the multi-fusion category. So from these examples, if you take the finite category of finite dimensional vector space, it's fusion category. If your group is finite group, then the vector G is also fusion category. And for finite group G, your G representation is finite. And also, like, yeah, these three, if they are finite dimensional or finite group. And also for operator algebra, so this BIM-M, sometimes it could be extremely large, but also sometimes it could be pretty small, especially like for all the fusion category can be realized for BIM of some 200 factor. But that is pretty different from the topic that we're doing today. All right. So anyway, so my topic today is the braided tensor category. So let me introduce what the braided tensor category is. So the braided tensor category is a tensor category with a braiding. So the braiding beta AB is a morphism from A tensor B to B tensor A. And this should be an isomorphism and satisfy the coherences conditions. That means if you braid A and C, you braid B and C first, and then braid A and C second, it should be same as you regard A tensor B as a single object, and this object braided with C. And also the naturality for morphism F from A to B, then going from A to B from F, and then braid B and C. It should be same as you braid A and C first, and then go from F to A to B. All right. And the other one, you braid A and B first, and then A and C. It should be same as A braided with B tensor C, and also this one. All right. So far, so good. And why do we care about the braided tensor category? So there are many sources of braided tensor category we can see. For example, 2 plus 1D topological order, or 1 plus 1D conformal field theory. I think Bingui is the true expert for this topic, so please reach out to him. Ultimately, because they are 3 categories, so braiding is naturally here there. And for topological quantum field theory, if you do a 3D topological quantum field theory, it's classified by modular tensor category, which is a braided tensor category with non-degenerate braiding, and also spherical. And another good reason is that von Jones discovered the Jones polynomial. Namely, if you start with the temporally Jones category, you define your braiding in this way, then you can regard all the links as a morphism from identity to identity. So every link can correspond to a number by using this this definition of braiding. You can unbraid them and eventually get a number. And the thing is a very good linking invariant, which can distinguish a lot of links. For example, this is left-hand or right-hand trifoil, and you can do the other one. And it turns out the Jones polynomial are different, so they're non-isotopic links. All right. So, okay. Next thing. So there are not many constructions of braided tensor category, and Drinfeld center construction is maybe the most famous one. So start with a tensor category C. Its Drinfeld center is a braided tensor category with objects A and beta A dash, where A is a object in C, and the beta A dash, we call the half braiding, is a bunch of isomorphism. Beta AB is isomorphism from A tensor B to B tensor A, such that they only satisfy half of the braiding condition, which means this is you braid A and B and A and C second, it should be same as you braid A and B tensor C, and also half of the naturality. All right, and this is a tensor category. So the idea of Drinfeld center is like there are many reasons to study that. Maybe one of the reasons is you want to imitate the center of algebra. We know that center of algebra is always a subalgebra of the algebra, but the Drinfeld center is not always a subcategory of the category C. In general, it should be pretty large, especially like to start with the modular tensor category, then it will be twice large as the, not twice, square the size if you care about the dimension of the category. Then, okay, so you see that we want to make A being the center. So we want A tensor B isomorphic to B tensor A by using this isomorphism. But it turns out we want to make it commutative, but it turns out it's really highly non-commutative. All right, especially your braiding is non-commutative, non-degenerate. All right, so, and also this Drinfeld center is one of known example for non-degenerate braiding, braided tensor category. All right. So Drinfeld center is very nice, and one remark that two fusion categories are Morita equivalent if and only if their Drinfeld centers equivalent as braided tensor category, and they can add the unitary condition on that is still true. And this remark only true for fusion category, and we don't know for general category whether this is true. We only have one way. The other way we don't know, but since our topic will focus on fusion category later. Anyway, so we provide another construction of braided tensor category. We call the centralizing structure. If A and B are two full replete tensor subcategory of tensor category D, a centralizing structure on the pair A and B is a family of unitary isomorphisms, UAB, from A tensor B to B tensor A, and the UAB is a morphism in D, in this big category. All right, and satisfy all the coherence that you see from the braided tensor category. But we only ask the braiding between the category A and B. All right, A and B. Here, though I'm saying f is from A to A prime in A, but since A is a full replete tensor subcategory, so you can really replace it by D. So yeah, it's still fine. And here you can replace by D. And then you can see, once we do the intersection of category A and B, which means you take the full and replace subcategory with the object both in A and B, this category will be a braided tensor category, which is also a subcategory, tensor subcategory of D. All right, and this is what we proposed. And now I'm going to talk about how do we get a braided tensor category from a single W star category. So suppose C is W star category. Remember, this just a category with an extra condition on your home space. All right, but you don't change that much. For example, the thing I listed for unitary tensor categories, these things are all W star categories. Yeah, but here we don't equip it with the tensor structure on that. So first we need a tensor structure. So it's natural to consider the end of C, the tensor category of endofunctors and natural transformations. And your tensor structure is given by the composition of endofunctors. All right, composition of endofunctors is a well-defined tensor product, and the tensor product is strictly associative. All right, so we get a tensor category and a C, and how do we get braiding? Well, we may think of, well, Drinfeld center, right? Yeah, it's a natural construction, but we propose the new construction called the local endofunctors. And this category is actually a full replete tensor subcategory of N of C with a unitary braiding. All right, and the way we construct that is using the thing we just say in the centralizing structure. All right. So before giving the full construction, I'm going to talk about the basic setting. Am I too fast?
It's good. So far,
okay.
so good.
Okay, I just can't see most people. Okay, let's carry on. So first, the Hilbert module structure. Suppose C is Cauchy complete. This W star category is Cauchy complete, which means it emits all the finite orthogonal direct sums, which means that the direct sum of two objects is still an object in this category. Like direct sum of Hilbert space is another Hilbert space. And also is orthogonal projection complete. Well, really, we don't really need this condition, but we put it here. It doesn't matter. And every Cauchy complete W star category should admit a canonical Hilbert module structure, which means for every object C in C and the finite dimensional Hilbert space H, there is an object H act on C. So how do we understand that? So if your Hilbert space is just C, one-dimensional Hilbert space, we require that C act on C is equal to self, unital action. And also, if H is n dimensional, then the Hilbert space is isomorphic to the n direct sum of n copy of C, right? But so we can regard H act on C, this object is isomorphic to the direct sum of n copy of the small c. But these two objects are isomorphic. The isomorphism is given by the isomorphism between H and the direct sum of n copy of complex number C. But don't say that these objects are equal, but they're isomorphic. And the isomorphism is given by the isomorphism of Hilbert space. All right. And this isomorphism, once we pick up those things, then there should be a canonical unitary associated between the K action and then H action, or H tensor K that act on C. All right. So if you just start with arbitrary C linear category, then it's naturally a VAC module. All right. Since this has a dagger structure, then it's Hilbert module. And from the Hilbert module structure, we can equip the end of C with the Hilbert module structure, which means for every endofunctor F, we have a canonical braided-like unitary natural isomorphism sigma FH, which means f of h action is isomorphic to h act on f. And we can provide this isomorphism, natural isomorphism explicitly. If you pick an orthonormal basis, EI, from help C to H, then orthonormal means EJ dagger EI equal to delta IJ. So remember, source and target, EI is from C to H, and the EJ dagger is from H to C. All right, dagger switch the source and target. So this morphism is from C to C, one-dimensional, and require that EJ dagger EI is delta IJ. And also the sum over EI dagger, this morphism is from H to H. This should be identity on H. All right, then we can define this natural isomorphism component-wisely by doing this. It's easier to see from the graphical calculus. So you pick EI dagger here, F of EI dagger act on A, and then compose by EI act on F of identity A. And this construction doesn't depend on the choice of orthonormal basis. So if you have another orthonormal basis, maybe epsilon j, then you put it here, epsilon j and epsilon j dagger, then EI dagger and epsilon j, this is in C, then you can move this to the top. And sorry, the dashed line is complex number C. All right, and we know that complex number act on the object is the trivial action. Then you can move this thing to here, then you can absorb EI and EI dagger. All right, so really this construction doesn't depend on choice of orthonormal basis. All right, so far so good.
Yeah, so A is a object in C.
Yeah, A is an object. Okay. It's natural transformation, right?
Yeah.
How do you define that transformation?
Yes. Okay.
Yeah. All right.
Mm-hmm.
And the second thing is the tau topology. So I'm saying that C is W star category, which means you have a topology, sigma strong topology on the Helm space. And so you can think of what is W star category. The endo Helm space is von Neumann algebra. But really, you don't really need to stick on this topology, but we only ask that whether this topology satisfies the following conditions. All right, it's not necessarily being sigma strong topology. So if you have bounded sequence of morphisms, Fn from A to B and Gn bounded non-bounded sequence from B to C, and we want that if Fn converge to F under the tau topology and Gn converge to G under tau topology, we want their composition G and Fn converge to GF under tau topology. All right, since we're a dagger category, it should play nicely with the dagger structure. So Fn converge to F under the tau topology, then Fn dagger should converge to F dagger under tau topology. All right, and in the end, we want the unit ball of each Helm space is completely metrizable. So every Cauchy sequence can have a unique limit. All right, so I mean the third condition is essential for our construction because we want every Cauchy sequence have a limit. All right. All right. And this tau topology also works for C-star category, which means you have the norm topology is still true. So this construction also works for C-star category. anyway, these are the setup. And now is the interesting thing that we're going to construct two subcategories of end of C with a centralizing structure. All right. Am I done? No, I'm sorry. One more thing. So approximating compute. So this is a commuting diagram. This is commuting diagram in category C. So if we have a morphism F from A to B, G is a morphism from B to D, H is a morphism from A to C, and K is a morphism from C to D, then this diagram commute means G compose F equal to K compose H, right? Since we are C linear category, so we can put this to the in the minus, all right? So GF minus KH equal to 0. Then what is approximating commute? If we do Fn being the bounded non-bounded sequence from A to B, GS is a sequence from B to D, Hn is sequence from A to C, and Kn is sequence from C to D. And this diagram is called approximate commute if Gn composed Fn minus Kn composed Hn, then no longer equal to 0, but we want they converge to 0 under the tau topology. All right, and we call this approximate commute. And also, we can do a similar thing for isometry. If F is isometry, then F dagger F equal to identity of A, right? As we said before. And a sequence of non-bounded sequence, Fn, is approximate isometric. That means the sequence Fn dagger F converge to identity of A under the tau topology. All right. Then with these things, approximate commute, we can talk about the so-called approximate natural transformation. So this is natural transformation, right? The transformation eta from functor F to G. That means for each object A and B, for every morphism from A to B, that this diagram commute, right? FA, GA, this A to A, FB, GB, A to B. All right, so this is commuting diagram for natural transformation. And what is approximate natural transformation? So it should be a sequence A to N from F to G, for any functor F and G. So for every morphism F from A to B, this diagram approximate commute. So A to N A, A to N B. This diagram approximate commute. All right. So I'm not saying that each A to N is a natural transformation. I'm not saying that. Just say these diagram for each A and B and the morphism F from A to B. And here we don't want F being the sequence, just a single morphism. This diagram approximate commute. All right. So far, so good.
Mm-hmm.
All right. And also, if you take those morphism being like norm 1, we just don't want these sequence once they converge to 0, right? Under tau topology, we don't or wish that these convergence being uniformly convergent. All right, just pointwisely for each A and B and F. This is approximate commute. That's enough. All right, we don't want to uniformly converge. That is kind of stupid. All right, or boring. And we call the approximate natural transformation from an identity endofunctor to itself as the central sequence. And this name is from operator algebra, but maybe for now it's just a name. Just call the from identity functor to identity functor, an approximate transformation called the central sequence. And then one may think that whether the endofunctor together with approximate tensor transformation can form a tensor category, because we already see that endofunctors with natural transformation form a tensor category. But whether it is true for endofunctor together with approximate transformation, the answer is not. All right, so it's not true in general. The reason is that by Ekman-Hilden argument, if your category is a tensor category, the end of one, the algebra of algebra end of one, end of the tensor unit, should be a commutative algebra. However, for approximate transformation, your algebra of central sequence is not commutative in general. So it failed to be tensor category. It's just a category. All right. In the end, we want to say approximate natural transformation eta n is isometric if each of eta n a is approximate isometric for each a. All right. So again, we want these things. So eta n a dagger, eta n a converge to identity, right? But we want this convergence not uniformly, just pointwisely for each a. All right. So that's good. So now we're going to construct. Now I'm going to construct two subcategories of n of c with a centralized instruction. And the first category is called centrally trivial. An endofunctor is called centrally trivial if all the finite dimensional Hilbert space and approximate natural transformation at n from h action to k action. So h action is actually a endofunctor, right? Because we already say that n of c has a Hilbert module structure. So once you do the Hilbert action, then it's still lying in this category, right? So this is an endofunctor, right? All right. Then the following diagram approximate commute. All right, which means the endofunctor is approximate commute with the Hilbert space action. So let's see, if you just talk about the natural transformation, no n, then this diagram is always commute because this is just saying that this is the Hilbert module structure, right? Sigma fh is a Hilbert module structure. So if there's a no approximating sequence, this is always true. Just saying this is a Hilbert module category. All right. But with the approximate natural transformation, this is not always true for all the endofunctors. So we just say the endofunctors satisfying this condition is called the centrally trivial. All right. So that's good.
Mm-hmm.
And another fact that if f is centrally trivial, if this diagram approximately commutes for all the central sequences. So again, central sequence means approximate transformation from identity functor, which means C action, complex number C to C. All right. And from this fact that it's easier to prove that the subcategory of centrally trivial endofunctors is a full, replete, Cauchy complete tensor subcategory. Tensor subcategory. All right. Tensor product of two or composition of two centrally trivial endofunctors is still centrally trivial. All right. So this is the first category. Second one called the approximate inner. If an endofunctor is called approximately inner, if there exists a finite dimensional Hilbert space H and approximate isometric natural transformation Vn from F to the H action. Namely, this diagram is just saying it's approximate natural transformation. And we want this also isometric. All right. All right. And then this pair, we call this pair Vn, the sequence, approximate transformation, and this finite dimensional Hilbert space is called the approximating sequence for F. So here, this is just existence. We're not saying that if F is approximate inner, there's a unique H and this. We're not saying that. We're just saying that exists. All right. And we say this pair is approximate sequence. And we can show that the subcategory of approximate inner endofunctors is a full replete Cauchy tensor subcategory of N of C. All right, which means tensor product of two approximate inner endofunctors still approximate inner. All right, so these are two subcategories we want. And recall that how do we define the approximate central trivial endofunctor? That means this functor is approximate commute with the H action, right? And approximate inner means your functor is proximally dominated by the H action, right? It's isometric, so proximally dominated by that. So by using the central trivial and approximator, so they should kind of have a braiding, but it seems like they are approximate braid. So exact our statement is if you have F being approximate inner and G is centrally trivial, and then we pick a approximate sequence, right, for F, because it's approximate inner, right? We have approximating sequence. Then we can see G compose F. We can go to G of H act on A, right? By using the approximate net transformation. Then using the H module structure, right? And then using dagger of the approximate net transformation can go back here, right? So by this procedure, you see that we already switched the order G compose F, which means G tensor with F and F tensor G. And it seems like this is a sequence, right? And we can show that this sequence is a Cauchy sequence. First, this sequence is a Cauchy sequence. Second, I'm sorry, Cauchy sequence. So remember, in our tau topology, every Cauchy sequence admit a limit, right? And we call this limit being UGFA. All right, and we can show that this limit doesn't depend on your choice of approximating sequence. All right, so this thing is unique. And we show that once we group up those UGFA, this will be a unitary natural transformation and satisfy all the coherences as the centralizing structure between the approximate inner and the centrally trivial category. All right. Therefore, once we do the intersection of these two subcategories, it's again a subcategory, but it's a braided tensor category, and the braiding is unitary. Sorry, this isomorphism is also unitary isomorphism. So what's it good?
Yeah, it's a
Okay.
non-trivial.
Yeah. Okay, let's carry on. So we get this idea from Kahn's original type. So maybe many people here not familiar with von Neumann algebra. So it doesn't matter. I'm not going to talk too much about that. So suppose M is a 2n factor, which means it's infinite dimensional trivial von Neumann algebra with trivial center. All right. All right. Then for the 2n factor M, Quan showed that the outer automorphism on M that both central trivial and approximate inner form a abelian group. That means intersection of central trivial and approximate inner automorphism that form a abelian group called the chi of M. And that year, it's really amazing result. That how can we get this result? And later, von Jones showed that on this abelian group, there is a quadratic form on this abelian group. But by the Allenberg-MacLean's argument, abelian group together with quadratic form should form a braided 2 group, which linearize to a unitary braided tensor category. So somehow we already have unitary braided tensor category, but just a little bit boring because all your object is kind of invertible, right? So can we get a more interesting or bigger unitary braided tensor category, generalizing this construction? So the natural way is to think of the module, the bimodule. If you start with an automorphism, it's natural to think of the bimodule, M bimodule, constructed by this automorphism, namely the space is taken by just this algebra M, but you twist your right action by active. Your action should go from alpha. All right. All right. And then the equivalence here is just the inner automorphism. So that's why I'm saying outer automorphism. So this is not just embedding, but up to the inner automorphism. All right. So it's natural to think of the bimodule version of chi. And Sorin Popa already defined the notion called the central trivial and approximate inner for Mn bimodules. And he showed that their intersection form a unitary tensor category called chi tilde of M. And our construction is just saying that if you take your W star category being the finite generally projective module of M, then the chi tilde of M is the n-log of this category. And also taking the dualizable part. And then we show that this category is not just a unitary tensor category, but also a unitary braided tensor category. All right. I mean, it's natural that for operator algebraists, they don't care about the braiding. Now it's pretty natural. Anyway, okay. So now people may ask, so far we define a very nice braided tensor category. Is that interesting? Right. Whether if it's always held the trivial category, the answer is this category could be extremely interesting. All right. Okay. So let's start with some old result for subfactor. So if n inside M is a finite depth, finite index, 2n subfactor. So 2n subfactor means inclusion of 2n factors. All right, for some condition. And finite depth, finite index means it's even part of standard invariant is a unitary fusion category. All right, finite depth, finite index means your even part of standard invariant is a unitary fusion category. All right, hopefully you remember what is fusion category. All right, like VAC G, RAC G for finite group G. All right. And the standard invariant means the category tensor generated by M as n bimodule. So you M tensor with n, another M, tensor with another M, finite many M, tensor over n, and then take direct sum and also the its component. All right. And this category is unitary fusion category. It's finite depth, finite index. All right. It's a really deep result for subfactor. And it's fair to say that many interesting or non-trivial unitary tensor category is from this construction. All right. Maybe Jone can say more about that. Anyway. And then for basic construction, if you start with the inclusion of two-n factor, we can do the basic construction called the Jones tower. And we take M infinity being the inductive limit. And for this algebra, if we put an additional condition that n inside M is non-gamma two-n subfactor, which means you can kind of control the central sequence in a more efficient way. Now we can show that the chi tilde of the single two-n factor, single algebra, is the Drinfeld center of your standard invariant. All right. And we have some corollaries. So first, this is a braided tensor category, right? Unitary braided tensor category, but also is a good invariant to distinguish these algebras. Just take this for example. If you start with two-n subfactors, non-gamma two-n subfactors with non-Morita equivalent standard invariant, then their Drinfeld center won't be equivalent as unitary braided tensor category. So these two algebras can be isomorphic, right? So we can see that we can construct a bunch of those things, non-equivalent or non-Morita equivalent tensor categories. Then these n infinity, m infinity, pretty different, and then usually it's hard to distinguish. Like if you take an subfactor, then these n infinity, m infinity won't be isomorphic. That's the first thing. Second, by Popa's subfactor reconstruction theorem or GGS construction, every unitary fusion category can be realized as standard invariant of non-gamma two-n subfactor. So every Drinfeld center of unitary fusion category can be realized as chi tilde of M for some two-n factor. For example, these, right? All right, so at least we can say all the Drinfeld center coming from operator algebra. All right. In the end, I'm gonna talk about maybe just the visual work on the higher symmetry for operator algebra. So operator algebras, namely C-star algebras, von Neumann algebras, just like algebras, form a two category. Your object are these algebras. One morphism are bimodules, right? And the two morphism can be bimodule intertwiners. However, by the looping hypothesis, a braided tensor category can be viewed as a three category with one object and one morphism. So essentially, braided tensor category has more symmetry or different kind of symmetry than the two category. But we see that our chi tilde of M is a braided tensor category, right? All right. And now we have many evidence to see that the three category of von Neumann algebra or C-star algebra should be a thing. All right. And which generalize this chi tilde construction. All right. Thank you. Thank you for listening.
Okay.